Hello everybody, this is Professor Iris Miano coming at you with section 8.4 lecture video. This is concerning day day 8 material. So yeah, we're just going to cover this one section for day 8, and then the next two sections in chapter 8 will go for day 9 stuff. Anyway, nothing that we're going to talk about here. Now for section 8.4, what do we want to focus on? Evaluating formulas. We're going to also solve some formulas and then introduce summation notation. But first, with evaluating formulas, what is the big idea behind this concept? It's basically just plug in values. Let's add some notes here. What color do I want? Let's do this teal blue. I love it. We're going to plug in given values for your variables and simplify. And let's go ahead and tackle this first example. In the instructions, substitute the values into the given formula, solve the remaining variable. Round to the second decimal place. I imagine they mean whenever relevant. It may or may not be relevant for all the problems. Okay? Okay, so looking at this first equation, you may notice that there's an x variable, and then there's this other x with a vertical line on top. Now, is that the same x as the original one given on the left-hand side of the equation? It actually is not. The incorporation of this vertical line on top, which is called a hat, or a bar rather. Actually, a hat, I think, is technically going to be the apex looking thing, a little bit of an angle on top. In any event, we can call it x bar. And it's a different variable altogether, and it has, if you look over here to the list of values associated with the variables that are going to have some number plugged in for it, it has its own distinct value compared to x without the vertical line, the bar on top. And then of course there's a value we're going to plug in for s, and so there's no value for z that's given in this cache of values that we're going to plug in, and so that'll indicate to the reader that we're going to be solving for the value of z. So every time you see an x, you're going to plug in 58.98 instead. So let's go ahead and start there. 58.98 plus x bar, or excuse me, equal, my bad. Oops, let's go ahead and erase that little bit. So yeah, sorry, let's start over. X is 58.98 equals x bar, which is 54.7, plus z times s. Z is our unknown, but it's being multiplied by the value of s that we're given, which is 2.6. Okay? And you are welcome to and encouraged to use your calculator. But I still wanted to show you the series of steps that you would take in order to solve this. So in a distinct color, let's do this like bright orange. I'm going to perform the operations that are going to isolate z now. Okay, so the first thing I'll need to do is take this 54.7 and subtract it from both sides. And that'll eliminate it here, which is on the way to my ultimate goal of getting a z totally isolated on one side of the equation, okay? But the first thing you need to do is do any a pose or s pose. If you remember from my previous lecture, that's addition property of equality instances or subtraction property of equality, respectively. And notice also that when I subtract these decimals, if I'm going to do it by hand, I need to line up decimal places, and also notice that there's a little empty spot and you can put a 0 right there if you want to. Or just grab your calculator, which is technically what I'm doing here to make sure that my calculations are highly accurate. So 58.98 minus 54.7, or 70, will leave me with 4.28. Oops, actually I want to move back to the teal. We'll erase this a little bit. 4.28. And now that is equal to, you can call this 2.6z if you want to, or you can keep it as z times 2.6 if you're really into that sort of thing. All right, so next we should divide both sides by that 2.6 value. 2.6, I'm going to try not to encroach too much on number 2 here. But I will recognize that this stuff is going to cancel right here, there and there, and I will be left with z in the next step, which I'll go ahead and put in this area here. And then I'm going to have to, you know, reach for my calculator, or I'm going to want to reach for my calculator in order to figure out what 4.28 divided by 2.6 is, because that's going to give me my value of z. So I'm just going to write that as a placeholder for what is being done in this next calculation. And my calculator says that z is approximately, so I'm going to do a little squiggly equal sign there, 1.6461538 dot 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 dot, you know, and it keeps going. So it's my job to recognize that the instructions say to round to the second decimal place. So in doing so, let me get back to my orange there, I'm going to focus on the second place value after the decimal, but then check in with the neighbor being the next place value's number to the right. And since it's a 6, the neighbor that is, that's going to bump my 4, which is in the hundredths place that I'm rounding to, or the second decimal place, it's going to bump it up by 1. So that means my final answer should be z equals 1.65. Okay? And I can use the equal sign because I'm being asked to do this rounding. Okay, so I want to find, you know, it's okay to put equals if you are giving a rounded answer, which by request. Okay, cool. So let's move on to the next one, which is going to be very tricky for us to look at notationally, because you may look at this, number 2 is what I'm focusing on, and see P and then in parentheses A or H. What does that mean? Is this function notation? No, it's actually associated with probabilities, which is something we'll get into as the very, very last section in this course. So we're going to just look at the notation right now, but not have any you know, formal demonstration on what it means, and that's okay. For our purposes, just recognize that P parentheses A or H has a specific value, and in this case it's 0.18. So we're simply going to substitute 0.18 for this P parentheses A or H. I can say one thing about it if anyone's curious. It's the probability that the events A or H could happen in a particular scenario. And then on the other side you have P of A, P and then A in parentheses, P with H in parentheses. Those are the individual probabilities that A would happen or H would happen. A and H being some events associated with a scenario. Okay, that being said, let's just go ahead and plug in the values in the, replace them for the individual parts that we have here. So instead of P parentheses A or H, we're going to put in 0.18. And that's the extent of what we're going to think about it with this. P of A, does that have a value over here? It is having a value of 0.07, so I'll replace it there, plus P of H. So this tells us, since no value is given for P of H, it's the last one standing, so that's going to be the value that we're going to be solving for. And what do we need to do in order to solve for it? Simply, we should subtract both sides by 0.07. Okay, it'll eliminate it here, and that'll give us 0.0 or 1 rather, excuse me. Oh, I should be more consistent with my color scheme here. Go back to teal. 0.11, and that's equal P of H. So if we were thinking about this in probability context, we would read this and say, oh, the probability of the event H happening, whatever event H is it has 11%, you know, probability of occurring. Not that we really care about that. specificity to this process here. We just want to work with evaluating formulas, and we have done it. So now we're ready to move on to solving for a variable. So you're not going to have the value for any of the variables associated with your formula that you'll be working with. You're just going to manipulate the formula such that you solve for the variable. So that's what I'm going to break down here as the idea. You manipulate the formula in order to isolate the variable. Now, what do you get to use in order to manipulate the formula? You get to use your properties of equality. So I'll put the acronyms for them just to save space in, writing. Addition property of equality, that's APO. Subtraction property of equality. Multiplication property of equality. And division property of equality. Okay, great. So, and there could be other tricks that could be useful, like distribution is sometimes appropriate. Other properties that you've seen happening in expressions or in equations could be useful or beneficial to this process. Okay, so let's keep it teal actually, and we're going to solve this particular formula for mu sub r. Yes, and I know some of you may be looking at this and being like, okay, what is this symbol right here in the numerator being subtracted off? That's a mu, which is basically the Greek letter for M. And then down below, you may notice there this little looking like an O with an extra little tail on it. That's a lowercase sigma, which is, believe it or not, equivalent to an S, a lowercase s in Greek. They're Greek letters, okay? And we have subscripts of R on those Greek letters, and then we have a subscript of 0 on this Z. So some weird stuff going on here. We just want to focus on being able to isolate, in this case, the mu sub R. So what do we do in order to isolate it? Well, we need to unpack what's going on over here on the right-hand side of the equation. And so go for the operation that is the least direct on the thing that you're trying to solve. In this case, it would be the division by sigma sub r. So I'm going to undo the division by sigma sub r in my first move. So let me go ahead and rewrite the problem. There's z sub 0 equals r minus mu sub r sigma sub r. Okay, so undo division by sigma sub r with multiplication on both sides of a sigma sub r. How do we feel about that? Hopefully that feels good and like a thing that you can totally do. We're just multiplying the same thing on both sides of an equation. So it's multiplication property of equality that I'm doing, that I'm implementing here. So these cancel, and we're just left with this on this side. Okay, and you could have sigma sub r and z sub 0 just kind of sit next to each other at this point because they're just variables being multiplied, the implied operations being multiplication. So it can look like that on the right-hand side. And then we're left with r minus mu sub r. Okay, now we might want to subtract r from both sides, in which case it'll look like this. Now it'll get eliminated here, but careful, there's no combining like terms over here. Even though r is a subscript on this sigma, these two variables have nothing to do with each other. As far as possible like terms situation going on here. They are not like terms. You have sigma sub r, z sub 0 minus r equaling negative mu sub r. We are so painfully close to getting mu sub r completely by itself. We need only either multiply or divide both sides of the equation by a -1, because we need to get rid of that -1 factor that's technically out in front of our mu sub r, the thing that we want to solve for. So I'm going to go ahead and choose to multiply both sides by a factor of -1. And it could look like that. And that's just going to change the sign and the operation of everything inside of this grouping symbol. And it's going to change the sign of this, this little guy out here as desired. So again, I'll continue over here. Let me just rewrite things with the -1 distributed all the way through. So that'll be a negative sigma sub r z sub 0. Now plus r is equal to mu sub r. And you can totally leave your formula like this, or you can choose to pancake flip it to have it read a little bit better. Reading from left to right, mu sub r equals negative sigma sub r z sub 0 plus r. It's fine, but or just leave it like this. Like, why give yourself extra work to do? As soon as you have mu sub r, or whatever the variable is that was you were being asked to solve for, as soon as you have it isolated completely, then you have solved the formula for that particular variable. You're done. Okay, moving on. Let's do this again, but for n sub 1 this time, which is right here in the original formula that we're given. U sub r equals 2 n sub 1 n sub 2 all over n. So just to be clear, n sub 1, n sub 2, and n without any subscript, those are all 3 distinct variables. The incorporation of subscripts does create separate variables, even though you're using the same letter n for each of those 3. Okay, so again, the first thing that I want to do is multiply both sides by n, because that's probably the least direct thing on the item that I'm trying to isolate. So it's like you gotta unwrap the present before you get, you gotta unwrap the box before you get, the present inside, kind of a thing. It's a multi-step process, and you're always going to, in the process of opening up a present, you're gonna work on your outermost layers first, and then dig, 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 until you get to the gorgeous present inside. That's my analogy for how you solve equations. It's like opening presents. All right, so hopefully that was put a little smile on your face. Let me just rewrite the problem, the formula that is, and then I'll be able to show you the result of my first step, which, as I said before, was multiplying both sides by n. That'll make these n's cancel out. And so I'll be left with n times u sub r equals 2 n1 n2. Now the only thing left for me to do is to get rid of these factors of 2 and n sub 2 on the right hand side, which I can do by division, and I can divide both of those factors at the same time. So I'll divide by 2 and n sub 2 on both sides. Resist the urge to want to cancel out these n's on the left-hand side. Okay, you cannot do that. You cannot cancel out an n with an n sub 2. Those are 2 separate variables, and canceling those out would be a big no-no. So let's cancel out these 2's though, and these n sub 2's. That's perfectly fine, and we're going to get n sub 1 alone on one side of the equation as desired. So now I'm ready to show you my final answer, n sub 1, and I'm going to go ahead and pancake flip the equation. I hope that's okay with everybody. So it reads really nicely, n sub 1 equals n times u sub r all over 2 times n sub 2. And that'll do it for that one. Now we're going to have another equation, formula rather, that we're going to solve for another variable, and then we're going to plug in some values in order to do some conversions. Okay, so that'll be parts 1 and 2 of this next example. So the example reads, let F degrees be temperature in Fahrenheit and C degrees be temperature in Celsius. A formula that describes the association between Fahrenheit and Celsius is C equals 5/9 times the quantity F minus 32. So this is a very useful and necessary formula for folks that live in the US, but they're from like pretty much anywhere else in the world, because most other nations go off of Celsius degree measurements, but the US is pretty stubborn and continues to do their temperature readings in Fahrenheit. So yeah, so this conversion formula will allow someone from outside the US to figure out what what the Fahrenheit will be given some, what the Celsius would be given some Fahrenheit. But let's say, you know, you're an American and you're visiting somewhere outside of this country, which due to the current times, from what I understand, is impossible. But that's neither here nor there. Let's just have some sort of a, you know, imaginary scenario here, and you're being given some degree measurements for the weather, and you want to dress appropriately, so you need to convert it to Fahrenheit. So solving for Fahrenheit in this first go right here is going to be helpful in that. Okay, so take your formula here and say to yourself, well, I need to free up this Fahrenheit, and it's in some parentheses with a 5/9 multiplier out front. So you could distribute through the 5/9 and work from there, because that will drop the parentheses, or you can perform this one little trick, which is to multiply both sides by the reciprocal of this fraction. That will get rid of the 5/9 in a way that doesn't require any messy distribution with a fraction multiplier, okay? So here I'll go. I'm gonna just kind of put a note here that I'm gonna multiply both sides by 9/5. 9/5, gonna just kind of write over it a little bit, and then that'll allow me to do some, what's it called, slashing right here, this 5 and this 5 slash, this 9 and this 9 slash. So I now don't need the parentheses on this quantity here. Cool. So at this point I have 9/5 C equals F minus 32. So I just have one more step that I need to take, and that's going to be adding 32 to both sides. Add 32. And this 9/5 C and the 32 constant term, they cannot be combined, so don't even try. Just go ahead and say that your F is going to be equal to 9/5 C plus 32. And you can call that done. All right, let's go ahead and box that up in pink, so pretty. Okay, so that takes care of part one. Part two is going to be, okay, now convert 15 degrees Celsius and 25 degrees Celsius using the formula that you just created, or modified the original formula to have it solved for F. So what do we get here? We get, so plug in a 15 for C is basically what we're doing here. Go back to this color here. We're going to have 9/5, multiply it by 15, plus 32. So what do we get? All right, this 15 is being multiplied by a 9/5, so it might be nice to modify it ever so slightly but not change the value. Just put it over a 1. So that way you can see that the 5 and the 15 are going to share some common factors, and those are going to slash away. So 5 divides itself the once, 5 divides 15 3 times. So you're actually going to have 27 right here. And that's what you're going to add the 32 to. So you're going to get, what's 27 plus 32? 59. 59 degrees Fahrenheit. Just to put some units on it and all that. Let's do this one more time, but with 25. So again, 9/5. This time the thing I'm plugging in is 25 plus 32. Just like I did with the previous one, I'm going to put that 25 over a 1, and that makes the slashing super clear. 5 divides itself the once, it divides 25 5 times. So that's going to leave me with a product in that first term. 9 times 5 is 45. And then I still have to add 32 to it. And what will I get? 45 plus 32 equals 77. 77 degrees Fahrenheit. Okay, great. Unit conversions complete. All good. Okay, let's go ahead and introduce summation notation, which, you know, is going to be one of the more challenging things that we talk about today. Summation notation involves several components. So I'll take this maroon looking color. We're going to have this new fun symbol. And this is the summation. It's a capital sigma. Again, getting into some Greek letters here. So it's the summation symbol. I'll also label it that way, summation symbol. And then inside some parentheses, or just in this space over here, you have what's called the argument. Now the argument is going to give you the structure of your sum. There's going to be a series of terms that are added together according to this structure dictated by the argument. Structure of the sum. The way that the summation problems are presented in this section, you're going to have a list of terms to, or excuse me, factors to plug in. List of factors off to the side, and they're going to have subscripts, and they're going to tell you which numbers to plug in for which factors among your terms that are being summed together. And it's all in the name. Summation means that there's going to be a series of terms added together. Now it's a little bit strange for me to just describe what's going on here ever so qualitatively. So let's just dive into a couple of examples in which we find the sum of a particular scenario here. So here we have mu being defined as some summation of a series of terms of the structure x sub I, p sub x sub I, p of x sub I, that is, okay? And you may notice that we have x sub 1, x sub 2, x sub 3, x sub 4. Furthermore, we have p of x sub 1, p of x sub 2, p of x sub 3, p of x sub 4. That tells you that this summation is going to go out to 4 separate terms, because that's going to be the highest subscript that you see. And furthermore, the structure of each term is going to be the first, like a p, or excuse me, an x sub 1, 2, 3, or 4, right? Well, it'll be x sub 1 for the first term, and then p of x sub 1 multiplied to it. Okay, so this first term that I'm going to write out is going to be eventually having the values 0 and 0.027 plugged in, multiply them together. So technically that first term is going to zero out. Okay, but what am I saying here? Let me go ahead and write the expanded version of this, and then we'll basically do a plug and chug, just plug in the values after we outline the structure. Okay, so again, each term looks like this. So that means the first term is x sub 1 times p of x sub 1. Then we're going to add, because it's a summation here, sum meaning add. The next term is going to be x sub 2 times p of x sub 2. The third term, can you guess what it's going to look like? X sub 3 times p of x sub 3. The next term after that, big surprise, x sub 4 times p of x sub 4. And I would do an x sub 5, but wait, we don't have an x sub 5 or p of x sub 5. So that's how we know that we are done writing all of our terms of our summation. So let's go ahead and, in this next step, replace all of these variables with their corresponding values as dictated by this cache of values. So here we go. X sub 1 is actually 0 times 0.027, because that's the value of p sub x sub 1. Okay, then we're going to add 1 times, what's p sub x of x sub 2? 0.189 plus x sub 3 has a value of 2. We'll multiply that by p of x sub 3, which is 0.441, and then we'll add that to 3 times p of x sub 4, which is 0.343. At this point, you would grab your calculator and go ahead and add all of these up. So 0.343, and you get that, plus, all right, 0.1989. Okay, so I get 2.1 because, okay, so I first did this. It doesn't matter which side you start from, actually. You can add, I mean, if you want to follow order of operations strictly, you would deal with this first, and you would see that it zeroes out, right? You guys see that? 0 times any number is just going to be a 0. So it's like nothing's there. And then 1 times whatever number, well, this is just a 0.189. Then you add the double of 0.441, and then you triple 0.343. So add all those numbers up, and you should get, like I said, 2.1. So that is the value of mu, and you can box that up and call it good on your effort there. Okay, so this one's relatively easy. Let's do one more example that's markedly more complex. Notice that we have MSE, which is some kind of engineering acronym that I don't even know what it is. That's not the point for our purposes here. We just want to practice being able to expand out what's going on with this summation. So some things to note here. It's only the I subscripted items that get repeated according to this structure, and then the entire summation gets divided by n minus k, which you see the values over here are just fixed values of 71 and 3 for the denominator bit. So let me go ahead and show you what the expansion looks like for this. Okay, and we're going to have one long kind of string. The summation stuff is going to go all up here, and then I can right away just put the n minus k, not repeat that at all. And why am I not repeating the n minus k with the summation? Because there's no I subscripts. The I subscripts are telling you, and also the fact that there's they're located, this n and this s business with the I subscripts, it's located in the argument area of the summation. So that tells you the structure of the terms that are being added together in the sum. Okay, so this needs to look like, I'll put brackets here, n sub 1 minus 1 times s sub 1 squared. So that's the first term of this summation. Then we're going to add n sub 2 in parentheses minus 1 times s sub 2 squared. Yep, this squaring right here is fixed. So all of these s sub 1s, s sub 2s, and there's going to be an s sub 3 as well, they all need to be squared. And then we need to add n sub 3 minus 1 of s sub 3 squared, and then close the bracket. Cool. So now that we have our summation entirely expanded out, along with this n minus k that's happening in the denominator, we are ready to plug in the corresponding values. So n sub 1, if you look here, is 22 minus 1 times s sub 1, which is 2 squared. Then we're going to add, what's n sub 2? 28, also minus 1, times, what's s sub 2? S sub 2 is 5. And then we square that, plus n sub 3 is 21, minus 1, times, what's s sub 3? It's 4 squared. And then n was 71. And k is 3. So n minus k is 71 minus 3. Now, running out of room here. I can put all of this in my calculator all at one time if I want to. We're going to have, what, 21 times 4. Just going to kind of speak out loud about what I'm doing here. And then we're going to add that to, what, 27 times 25. 27 times 25. Hold on, I already messed it up. Okay. All right, so let me start over here. 22 minus 1 is 21. So the first term is going to be 21 times 2 squared, which is 4. So that's 84. Okay. And then we'll add that to 27 times 25, which is 675. Big number there. Plus 21 minus 1 is 20 times 16, which is what 4 squared is. So 20 times 16 is 320. Okay, so I'll add 84, 675, and 320 in the numerator, and I'm going to divide that by what's 71 minus 3. That's 68, if I'm not mistaken. Okay, so that numerator, 84 plus 675 plus 320 is 1,079. And then I'm divided by 68, which is, yeah, some long decimal number. Round to the second decimal place. Okay. So I'll write down what I get from my calculator. It is 15 point, and I'll do a little squiggle equals, saying it's approximate. I'll write down a bunch of significant figures just so we can practice once again the rounding. 6, 4, 7, like blah, blah, blah. It goes on and on. We only really need to focus on the 3 decimal places. We need to focus first on the second decimal place because that's what we're rounding to, and then check in with the neighbor to see if we bump up by 1 or stay the same. So we're going to bump up by 1. So that means that MSE is equal to 15.87, rounding to the nearest second decimal place. Okay, and that's a wrap on section 8.4. So you're going to, in class, get plenty of practice on dealing with evaluating formulas, solving for particular variables and formulas, and summation notation. And I'll be there to help you with your small group discussions. Very good. All right. Thank you so much for your attention.